So I said a little bit about this last time, so I'll try to catch up to speed quickly. So what I want to do today, because I need some topological ideas, is just provide a topological description of what is a figure. And the description is in the form of the theorems stated in this document. So volume behaves well under the operation of taking union and taking interior and taking point. Where what is the interior? A point is interior to a set if you can find a little epsilon neighborhood, delta neighborhood, so that whole neighborhood is contained in the set. And B minus is resolved under that operation. So that is an example of an interior point. A point is in the closure of a set. We'll put dashes to indicate that those points aren't actually in the set. So there's a point which is a closure point. If you take any little delta neighborhood of the set, there's lots of things out of that point. There's lots of things in the set within that delta neighborhood. So those are the two topological operations we'll talk about. And I mean, visually, you can see that if you have a picture that looks like reasonable, if you like shave off all the non-interior points from the set, you shouldn't change the volume by much. And this result says that even if you have a terrible set, a set that's not a figure, you won't change the inner volume at all. If you add all of the points that you need to add to get the closure, so in this picture that means like adding in all of these points, you don't change the outer volume. Oh, so what do you think? If you start with like an honest to God figure, the actual volumes won't change. So, armed with that, the topological description of what is a figure, well, takes the form of this. If you start with any bounded set, then the difference between the inner volume and the outer volume, right, so that's exactly the difference you need to be zero for a thing to be a figure, is given by the outer volume of the boundary. And, as a corollary, figures are sets whose boundaries have no outer volume. They can have some inner volume. Well, no, if they have no outer volume, they have no inner volume. So that's our goal. And so far we had started doing a little bit of analysis of just rectangles. In particular, the lemma we need is if you start with any rectangle and any slightly littler rectangle, where what does slightly littler mean? All of the endpoints of all of those intervals contain those intervals, and they contain them properly. For each I, AI is less than CI, and DI is less than BI, so you get a picture like that. Then the claim is that every point in Q is interior to R. So maybe just to come back up to speed, let's talk about the structure of that proof. So if you want to prove that Q is interior to R, well, how should a proof of set containment be formatted? What do you need to show if you want to show a set is contained in another?
Pick something Q.
And what do you need to show?
It's in R.
What?
Yeah.
Oh, but the interior of R has a definition. What does it mean to be the interior? What does it mean to be in the interior?
It's in the intersection of all open sets contained in R.
Union of all open sets contained in R.
Oh yeah, sorry.
But in the case of a metric space, you can phrase that as there exists some delta bigger than 0, such that the ball centered at P of radius delta is contained in there. Okay, but how do you prove that set containment? You consider anything in this ball and show it's in that rectangle. This rectangle is a product of a bunch of intervals, so we need to show a bunch of inequalities. So that's the plan of attack. And what we came up with last time by just looking at this picture is that a delta, which is the min of all the differences between the CIs and the AIs, and the differences between all the BIs and DIs, of all choices of I's, So that's like a set containing 2 n elements. Oh, well, that's a finite set, so I'm justified in saying min and not inf. And it's also important that I say min. The min of a bunch of positive numbers is still positive. Does the inf of an infinite collection of positive numbers need to be positive?
No.
No. So it's important that this be finite. So trying to do a result like this in the case of an infinite dimensional space, which we won't talk about in this class, because that's a kettle of fish that I don't want to cook. Yeah, it's more complicated. So let's do this then. So there's choice of delta. I need to prove this set containment. So let's consider any x in that ball such that p of radius delta. What is it that we need to show if we want to show that x is in this set R? We need to say let x be in b p delta. We need x to be in that rectangle. So I guess that means that we need to show that for all I, ai less than or equal to x, less than or equal to bi. That's what we need. Let's try to get there. So let's see what we know. So I get to assume that x is in the ball centered at p of radius delta. Then I claim that for every I, pictures help. There's p, there's x. So I know that this length is less than delta. Well, if you know that the length of the hypotenuse of a right triangle is less than delta, then what can you tell me about the length of each of the sides? Very less than delta. And the same thing is true even if you go up to dimension. So the length of each of those individual lengths is less than all the length from x to p, which in turn is less than delta. Now, I need to get this inequality to happen, so let's try to get that. And there's lots of space on the next page, but I think that I maybe don't need it. So let's just try to get any facts we can about x. And let's start with this. Let's start with this. Since absolute value of xi minus pi is less than delta, what inequality can I get? Solve that inequality for xi on SID. How big could, so if the absolute value of x minus p is less than delta, then what can you tell me about just xi minus pi? What numbers does that have to be between?
Negative delta and positive delta.
Negative delta, positive delta. So because that is true, with absolute value bars around it, I conclude that negative delta is less than xi minus pi is less than positive delta. So, like, you know how to solve that for pi, right? What's the result when you solve that for pi?
Yeah, minus delta less than xi less than pi plus delta.
Thank you for even answering the question that I should have asked instead of the question I did ask. Because I said, like, solve for pi, but that's not the thing you want to do anyway. All right, cool. So there's the inequality we get. That's not quite the inequality we need. But what bounds do we have on delta? Delta is the min of a bunch of things. So it has to be at most as big as each of those things. So what? I mean, there are 2 n bounds written there, but I think for each choice of I, we only need 2 of them. Which 2 bounds seem useful?
Probably the ones with I.
Probably the ones with i's. So let's combine this by saying since delta is less than or equal to bi minus di, and delta is less than or equal to ci minus ai, let's use control of P. What do I know about P? What set is P in by assumption?
Q.
And I mean, I guess that was like 48 hours ago or something. But there it is. It's in Q. Q is by definition a rectangle. So let's see. Since P is in Q, which is a product of a bunch of CIDIs, what can you tell me about each PI? Each PI is between CI and DI. So I guess I do have to use the space on the next page. Happily, there's lots of space on the next page. So out of that, I can conclude that CI less than or equal to PI less than or equal to DI. And I guess it's unfortunate that the two inequalities that I'm about to use are on different pages. So there's one to use. Combine that with this. And I think that I'll just copy that down with a little space to the left and right. So, minus pi minus delta is less than or equal to less than xi is less than pi plus delta. And let's use those bounds. So since pi is bigger than or equal to ci, what can I conclude?
Ci minus delta less than or equal to xi less than or equal to probably di plus delta.
Yeah, it should be di. But that's still not what we need, is it? Now let's use what we know about delta. So let's see. Well, full stop. I know that delta is less than or equal to ci minus ai, and delta is less than or equal to bi minus di. Yeah, less than or equal to. So, ci minus delta. So that means instead of going left just by delta, I could go left by ci minus ai, and I would be forward to the left. So ci minus ai is less than xi is less than pi plus di, which is less than delta I plus delta is less than delta I plus bi minus di. Oh wait, but what does that reduce to?
Yeah, it was bi.
From that, does it follow that xi is in the interval from ai to bi?
Yeah.
So xi is in ai to bi. In fact, I could have open things there, but I don't care.
Should be bi.
Yep. Yep, it should. Did I at least say bi? Doesn't matter. The recording will know, but I certainly won't watch the recording again to check. So if xi is in there, so x is in the product of all of these ai's to bi's, which is exactly the definition of R. So ball centered at P of radius delta is contained in R, and P is in the interior of R, which is exactly what we needed to show. How does everybody feel about that? So, on the one hand, like, that was a nice little warm-up for, like, how do you think about interiors? And we'll make use of it in the next result, which will show, well, it's trying to show theorem 5, but it's only trying to show theorem 5 in the special case of rectangles. Because what do you think? If I take a closed rectangle and take its closure, what should the result be?
Same thing.
Same thing? And pictorially, that kind of makes sense, right? If I give you a rectangle, there it is, and ask you to take its closure, it's only going to contain everything that was already in the rectangle. But if I take a point not in the rectangle, is that a closure point for the rectangle? You can find little delta so that delta neighborhood doesn't intersect the rectangle. So the closure of a rectangle is that rectangle. The interior of a rectangle is the product of the open intervals from AI to BI. So let's prove this. Let's prove that if you have any rectangle, then the interior of that rectangle is a figure, and the volume of the rectangle is the same as the volume of the interior of the rectangle. So here's how we'll play the game. Let's take M to be the min of all the AI minus BI, so the shortest of all of the side lengths of the rectangle. I'll take that and divide it by 2. That gives me a delta. I will now assign Q, sub delta, to be a bunch of intervals, each from AI plus delta to AI minus delta. So that's supposed to be a rectangle with the side lengths parallel to the right side lengths. Happily, that's not being recorded, so. So there's another rectangle which is all totally interior to R. Every point in the green rectangle is interior to the big rectangle, by the theorem we just proved. So this rectangle is contained in the interior to our circle, is contained in R. So let's appeal to monotonicity. So if Q delta is contained in the interior, then which is bigger, the volume of Q delta or the volume of the interior? Right, the interior. Yeah, the bigger set has bigger volume. And I guess kind of I'm noticing here that volume is the same as volume minus when volume is defined. Which is bigger, the inner volume or the outer volume? Outer volume. And the interior is contained in the whole set. So which has bigger volume, the interior or the whole set? Whole set. And notice that I don't want to assume that the interior is actually a figure. So that's why I have both a B minus and a B plus. Do you think that the interior of a rectangle is probably still a figure? It seems likely. It seems like a set that's not terrible. So let's write down some things. We have a definition for the volume of a rectangle, right? And we've even checked that it agrees with the definition of the volume of the rectangle that we get by assuming this thing for the volumes of rectangles. So this volume is the same thing as the product of all of these BI minus AIs, except it's really AI plus delta to BI minus delta. So that has to be less than or equal to, Chris. Numbers are not subsets of other numbers. Numbers can be less than other numbers. The set can, well.
In a way. You're not incorrect. Maybe it's correctness, it's math.
Well, you can build number theory by starting with set theory. And if you do, then really everything is a set. So nice, let's take a limit as delta goes to 0. What's the limit of the quantity on the right as delta goes to 0? Yeah, there are no deltas, right? What's the limit of this as delta goes to 0?
I think you're right. Shoot.
There are no deltas, right? What's the volume of the what's the limit as delta goes to 0 of the volume of the interior of the parasol?
Shouldn't change.
Shouldn't change, no deltas. What's the limit of the leftmost thing as delta goes to 0?
The far right thing.
Yeah. Oh, hey, so what can we conclude?
They're all equal.
That v minus of our sock is equal to v plus of our sock is equal to, well, the volume of the original rectangle. Oh, so notice, like, the fact that these two things are the same is exactly what it means to be a figure. So, nice. People feel pretty good right now? So let's get to one of the actual theorems of the day. If you have any set x, and this really is kind of one of the, this theorem is going to be the most technical thing in this note packet. For any set x, the inner volume is the same as the inner volume of the interior, the outer volume is the same as the outer volume of the closure. Let's try to prove it. Who remembers what the definition of inner volume is?
Second time, no.
We get the soups and the
Strike that.
So v minus is supposed to be like an underestimate, right?
Yeah.
And so,
it'd be like the soup of all the sum of inner volumes.
Yeah. Oh, yeah.
and similarly, v plus is the int of all of the v pluses, indexed by the same thing. So let's just try to study an arbitrary v plus and v minus. And like that always gets a little bit index heavy, but I think it won't be so bad. Let's do that. So let's start with this. Look back in this note packet. What does proposition 2 say?
Interiors containing sets contained in enclosure.
Interior is contained in set containing enclosure. And I claim that I'm going to use the monotonicity of volume to make a conclusion. What conclusion can I make out of monotonicity by using those two facts?
On the left is bigger. And on the right is bigger than the second one.
Yeah. So that, I mean, in some sense, I'm like halfway done. But if I want to prove one equality, I need to prove two inequalities. And I need to prove two equalities, so I need four inequalities. There are two, so halfway done. So in order to get the other half, let's consider any bounding rectangle R for x and any subdivision delta of R into rectangles. Now remember, we define the integral by taking a subdivision into arbitrary figures. We compute volume by taking a subdivision of a bounding rectangle into smaller rectangles. Let's see. Do you believe that if I start with the bounding rectangle for a set, I also have a bounding rectangle for the closure?
It's smaller.
The closure is bigger.
Yeah, but I want to
No,
see
I mean
that homework.
I meant the other way around, but yes.
So like on the one hand, like I could just declare R to be a bounding rectangle for the closure. Then maybe you would want to challenge me, like if a set is if a set's bounded, why should its closure be bounded? But that definitely, I think you believe. I mean, let's see. If P is in X bar and X is contained in a rectangle. Nope, that's not what I want. I do use product for like the Cartesian product and for multiplying numbers, but in this case I mean that. Well, what does it mean to be in X closure? Is that for every delta bigger than 0, there exists a Q in X cap. Maybe I'll even index it. Let's call it X. X delta in X intersect. So that means that this X delta is in there. So that means that each AI is less than x delta sub I is less than or equal to bi. Oh, but this is within an arbitrarily small delta neighborhood of p. So do you think you could like take a limit and put a pi there? Like maybe you'd want to say some all lots, but that's the idea. Now what do you think? Do you believe it and maybe even see how to prove it? Cool. So R is also a bounding rectangle for the closure. The interior is small r, right? So R is automatically a bounding rectangle for the interior. And the boundary, well, isn't mentioned here, but it follows. All right, so let's try to compute V minus of x delta and see if we get the same thing as the interior. So let's let J be an inner rectangle for x corresponding to the subdivision delta. So if J is an inner rectangle, what can you tell me about J as compared to x?
Has a smaller volume.
Yeah, but I mean, even without volumes, it's a subset. That's true. What you said is true. If J is contained in x, do you think the interior of J is contained in the interior of x?
Yes.
And maybe this, I'll even like try to take an aside to explain why. So let's let P be in the interior of J. Was it last semester when someone suggested I should start calling my sets J so that let P be in X would become let P be in J?
Oh god. I don't think so.
Okay.
Pretty good though.
Yeah, I think so. I'll say, so let P be in the interior of J. I need to show that P is actually in the interior of X. What does it mean to be in the interior of J? That's true. If you took that mindset, that would mean that P is in every open set that's contained in J. Well, but every open set contained in J is also an open set contained in X. So that would be one argument. But maybe I'll say this instead. So there exists a delta bigger than 0, such that the ball centered at P of radius delta is contained in J. So this is the same thing. I'm just only using open sets and no balls. Like you have a metric structure, so use it. But wait, what did I assume about J? Well, no, what do I just know about J? Have I just shown that every ball, that there exists a delta bigger than 0 so that the ball centered at P of radius delta is contained in X? So P is interior to X. Nice, so that out of the way. Let's use this to achieve something. So there's some like instructions for what to do on the left. Let's figure out what these instructions actually mean. So I want to study the volume, inner volume of X corresponding to the subdivision into rectangles. What's the definition of V minus of X comma delta? Maybe not in like summation notation, but like the idea of it.
Area of all the rectangles contained
Yeah, take
of the subdivision.
all of the rectangles in the subdivision that are contained in X. So that means I'm going to take a sum indexed by J in our rectangle for X. And what is it that I need to add up for all of these J's? Their volumes. According to lemma 4, what is the volume of J the same as? By flipping back to look at lemma 4.
Interior of J.
Yeah. So notice, I have the interior of something in play now at least. All of those J's are well, they're not by assumption disjoint, but they have pairwise intersection equal to 0. volume of pairwise intersection is 0. So that means instead of computing the sums of the volumes of the interiors, I can compute the volume of the union of the interior. Everyone happy enough? And that's a V because it is, well, each of those J socks is a figure. We check that. Is volume the same as inner volume if you have a figure? Yeah, that's what. And I've just put that volume minus there in order to make the next step more obvious. That union, each of those J socks we've shown is contained in X sock, right? So is the union contained in the interior of X? Right, if each member of a union is contained in a set, then the union is contained in that set. So since this is contained in X as a subset, that means this must be less than or equal to V minus of X. So let's try to think about what we've just shown. We've considered absolutely any subdivision, and we showed that V minus of X delta is less than or equal to V minus of X sock. So that means V minus of the interior of X is an upper bound on the set of all inner sums for the volume of X. V minus is the least upper bound, so it's less than every upper bound. So what inequality can we conclude? If this is an upper bound, and that's the least upper bound, which one is bigger?
No.
Yeah. We conclude V minus of X sock is bigger than or equal to V minus of X. Is that the opposite of the inequality that we already proved? Yeah, there's still a V minus there. Exactly as we needed. Let's try to do the same thing for the closure. And so I'll try to do a very similar game. Some of it will seem slightly backwards. So what it'll be inspired by is the idea of, well, instead of taking the outer volume of a set, let's take the inner volume of a bounding rectangle minus the set. That should be the same as like the volume of a rectangle minus the inner volume. So we haven't proved that, it's true. But we'll be inspired by that idea. Instead, we'll try to compute the inner volume of the complement of the set. So let's play the game. V plus of X comma delta is equal to the sum of over all J an outer rectangle of X delta. So they're outer rectangles. That sounds like they're exterior to X, but that's not what I mean. I just mean they have a point in common with X. J is an outer rectangle for X comma delta. We're going to add up the volume of J. And I said I want to, like, instead of adding up, I want to think about the volume of the complementary region. So let's get to the complementary region somehow. So if I add up all of the volumes of all of the rectangles in delta, that gives me the volume of R, right? So let's take the volume of R, that's the sum of all of the rectangles, and let's subtract out the volume of all of the non-outer rectangles. That makes sense? Let's do that. Minus the sum over all J not in, for emphasis, there's the not in green, out of X comma delta volume of J. What does lemma 4 say I can do with that volume of J?
Make it the volume of the closure.
Make it the volume of the interior.
Interior.
That's also true, but volume 4 was only about interiors. So that's the same as the volume, the sum, over all of these J's. I'm not going to write that because it's going to take up too much time and space. Oh, nice. So let's explore that just a little bit more. So that's the same as the volume of R minus, and I'll re-express it this way, the volume of the union of all of these J socks, where J is not an outer rectangle. Let's see, is this union a subset of R?
Yeah.
Well, we've taken the volume of a set difference. And it's particularly easy when this is explicitly a subset of that. That's the same thing as, oh, well, that was supposed to go there. That's okay. This was supposed to go here. That's the same thing as the volume of R minus the union over all J's not in out of X delta of the interior of J. So I've just done a bunch of manipulation to re-express the outer volume as the volume of this explicit set. And I don't know, I think a picture would help. So there's a bounding rectangle. There's this set X. So to compute the outer volume, I'm going to take the volume of the whole rectangle. I'm going to take the whole rectangle, and I'm going to cut out the interior of that rectangle, the interior of that rectangle. I'm going to cut out the interior of that rectangle and the interior of that rectangle. Oh, yeah. Maybe this one too? Hard to tell.
Sure.
So here is what my claim is. So let's look at what I'm actually taking the volume of. So I'm taking the volume of stuff that isn't circled in orange. Is every closure point of the set X not in orange? That's a weird thing to say. So if I take a point that is in X, could that point possibly be in one of the orange pieces?
No.
And in fact, I claim that's true for the closure also. I claim that X is a subset of R minus the union over all J not in out of X delta J sock. Oh, nice. So this is like a set containment proof. How do you prove a set containment thing?
Take something in the left.
I don't want to say X because there will be another thing there soon. P? I don't think P has a job yet. Let P be in the closure of X. What does that mean?
The intersection of all closed sets.
I only remember the topological definition, not the metric space.
So let's draw a picture. So what does it mean to be in the closure? Means that if you draw a little circle around that point, there should be stuff in X that's in that level. So let P be an X. So for every delta bigger than 0, there exists an actual honest-to-God X in X intersect the ball centered at P of radius delta. So that's what I know, and I want to show that that point is in that complementary thing. Let's see, is this point X well, let's look at that point P. Is that point P automatically in R? R was a bounding rectangle for everything. P is in R as R is a bounding rectangle. So that means that I would be happy if P is not in this union. That's like a negative. So how about if I try to make a proof that proceeds by confirmation and suppose that P is in that union? So let's I'm going to box this and decorate it so that I can refer back to it. Let's suppose that P is in the union of all these j's not in out of x comma delta of the interior of J. So let's try to figure this out. What's the only way a point can be in a union of a bunch of sets?
It's in at least one.
If it's in at least one. So P is in the interior of J for some J not in out of x delta. So I guess there are two things to put together. What does it mean for P to be interior? What does it mean for x to not be an outer rectangle? All right, let's do one at a time. No, this one first. What does it mean to be in the interior of J? So as P is in the interior of J, there exists a delta bigger than 0, such that the ball centered at P of radius delta is totally contained in J. What does it, well, let's try, that's like a not. What does it mean to be an outer rectangle?
The intersection is empty.
It's not empty.
Wait, it's
Yeah, so
it's
I
an
asked,
outer rectangle. It's not empty.
I asked it without the not,
Oh.
and then I was going to put the not back. So what does it mean to be an outer rectangle? It means that J would intersect X. So what does it mean to not be that? It means the intersection. As J is not in out of X delta, J intersect X is the empty set. Wait, so if that ball is contained in J and J has no points in common with X, could that ball have any points in common with X? So the ball centered at P of radius delta intersect X must be contained in J intersect X, which is empty. So we've just shown that there exists a positive number delta, so that the ball centered at P of radius delta has no intersection with X.
That sounds contradictory enough.
That sounds contradictory to like an explicit thing, right? Green star? That's why I labeled it. I've got more space. Oh, I actually don't. This contradicts green star. So, therefore, it must be that X bar is actually contained in that. So, there's a justification for that set containment. But I want to go over to the world of volumes. So that means that the volume of X bar must be less than or equal to the volume of that set. Well, you won't be able to read it if I write there anyway, so I'll just scribble.
You bring a paper down.
Oh yeah, all the more reason for me to scribble. You couldn't tell what I was writing. So the volume of X must be less than or equal to the volume of that set that we had. Oh, but wait, the whole point is that volume of that set was the same as that. So, what did we just show? We have shown that V plus of X is a lower bound on the set of all upper sums for the volume of X. What can we conclude then? So actual V plus of X is the greatest lower bound. That is a lower bound. So which is bigger?
Plus a regular.
V plus of regular X. So v plus of regular x is bigger than or equal to v plus of the closure of x. But have we already proven that the opposite inequality is true? Thus, v plus of x is the same as v plus of x bar, completing the proof. So I've got slightly less than 5 minutes. I'd be really terrible in this room if that clock didn't work. Every class would go for an hour and a half.
We'll all set phone alarms.
I guess you would have to at some point.
Or maybe we'd start scoring with you. 145, set them off. 140.
Oh yeah, that would be clever.
105, set them off.
Guess it's time to go. So the next result is that for any set x, if you take the outer volume minus the inner volume, you get the volume of the boundary. And that seems about reasonable, I think. Certainly if you take like the outer set and you subtract the interior, you'll get the boundary. There's something. So here's the way that I'm going to proceed. So if I want to compute outer volume of the boundary of x, let's consider any subdivision of a bounding rectangle and try to compute the outer volume of the boundary x corresponding to that subdivision. Well, then if I want to compute the outer volume of the closure, well, I want to compute the outer volume of the closure with respect to that set of bounding rectangle, that set of outer rectangles. And if I want to compute the inner volume of the interior, I want to do that. So let's try to show that. And the first containment will be like really easy. Let's try to show that the set of outer rectangles for the boundary is contained in the set of outer rectangles for the closure intersected the set of inner rectangles for the interior. So let's let J be an element of out of boundary x, comma, delta. What does it mean to be an outer rectangle for a set? That has a point in common with? So J intersect boundary x is not equal to the empty set. What's the definition of the boundary of a set? You can look at the front page again if you want to. And once you look at that and like you tell me what it is, then I'll like draw a picture that says cross this and like this.
Everything that's in the closure is not equal to.
Yeah, I mean, we just have a different, the same definition in a different setting of what closure and interior are. So J intersect x bar minus x sock is not empty. Well, wait, so could J intersect x bar possibly be empty?
Repeat the question.
Could it possibly be that J intersect x bar is empty? No. Because it intersects a subset. So as J intersect x bar is not empty, J is in out of x bar delta. Now we need to show that J is not an inner rectangle. Yeah, J is not an inner rectangle for x sock. Well, let's expand this out a little bit. So, because this is not empty, it must be, this is the same set again. J intersect x bar minus J intersect x sock is not empty. Yeah. So could it possibly be that, let's see what would happen. I think I'll leave this out. There's some freestyling going on. So let's see, if J were an inner rectangle for x soc, then what could we conclude? What does it mean to be inner?
There's some delta such that all is extra.
That's the definition of interior. What does it mean to be an inner rectangle? It just means it's a subset.
Yeah, I agree with that more.
So J then is a subset of x soc. But wait. J intersect x bar minus, but there exists a point P in J intersect x bar minus x socle. Could that point P possibly be an x socle? Nah. So J is not a subset of x socle. Thus, J is not an inner rectangle for x socle with respect to the subdivision delta. So, at this point I'm out of time. The other containment will be the one that actually needs some ideas. That's where there's actually some words written down. In fact, it will take me a decent amount of time to prove that set containment. It will take me until about there. So it'll take me basically the rest of the proof to achieve that. Once I have that, I can get all of the volumes of rectangles to be as close as I want to the actual honest-to-God volumes I wanted to know. So that'll complete the proof. Cool. So we'll pick up on this next time.
I'm so bad. Can you go back to the page I did for the last one?
Yeah. So
Yeah, okay.
yeah. So this point is a point that's in J,
Yeah,
but it's not in X.
yeah, but because of that, we can't JB.